Over the years, the number of known elements has gone up from 37 to 118, making it difficult to study them and their innumerable compounds individually. Hence, scientists started organizing them in a systematic way, such that those with similar properties were placed together and those with dissimilar properties were kept separate. After years of experiments and observations, scientists came up with the concepts of periodic table and periodic law. It classified elements in rows and columns such that the periodicity in their properties, that is, the reappearance of similar properties at regular intervals, could become apparent. A periodic law defines the periodicity in the properties of elements in a periodic table. This classification not only helped scientists in comprehending the properties and chemistry of existing elements, but also in predicting the properties of elements that were yet to be discovered. Since 19th century, scientists have attempted to classify elements using different approaches. For example, in 1817, German scientist Johann Dobereiner noticed similarities in the physical and chemical properties of elements and observed that these elements formed groups of three. He called these groups triads. He found that the elements in each triad, when arranged in the increasing order of their weights, demonstrate that the atomic weight of the middle element is the average of the other two elements. This he called the law of triads. For instance, in the triad of soft, reactive metals, lithium, sodium, and potassium, the atomic weight of sodium, 23, equals the average of the atomic weight of lithium, 7, and potassium, 39. Similarly, calcium, strontium, barium, and chlorine, bromine, iodine also formed triads. However, as Dobereiner's law of triads seemed to work only for a few of the known elements, and hence it was dismissed as mere coincidence. In 1862, A.E.B. Deschamps-Courtois arranged the then known elements in order of increasing atomic weights and made a cylindrical table of elements that displayed the periodic reoccurrence of properties. Deschamps-Courtois' periodic table was important because he was the first person who arranged all the chemical elements in the order of atomic weights. Chemists did not give his discovery its due attention because he used geological rather than chemical terms. Slowly, people recognized the significance of arranging elements based on their atomic weights. In 1865, an English chemist, John Alexander Newlands, propounded the law of octaves. According to the law of octaves, when elements are arranged in the increasing order of their atomic weights, the properties of every eighth element are similar to that of the first element. This trend resembled the octaves in music, wherein every eighth note is similar to the first note. Hence, the name law of octaves. For example, in Newland's periodic table, the 8th element after lithium is sodium, and the 8th element from sodium is potassium. All these elements are similar in their chemical properties. However, Newland's law of octaves was not found to be true for new elements found after calcium. This led the German chemist Lothar Meyer to develop a table of the elements that closely resembles the modern periodic table. He observed a periodically repeating pattern of chemical and physical properties against their atomic weight, while analyzing atomic volume, melting point, and boiling point of elements. Unlike Newland's, Lothar Meyer observed that the length of that repeating pattern was not constant and there was a change in the length, and so created a periodic table based on the increasing atomic weights as given on stage. Unfortunately, his work was published after the work of Dmitri Mendeleev. Hence, Mendeleev is considered the father of the modern periodic table. In 1869, Russian chemist Dmitri Mendeleev published a periodic table and corresponding periodic law of 63 elements known at that time. Mendeleev's periodic law states that the physical and chemical properties of the elements are a periodic function of their atomic weights. Mendeleev created the periodic table by listing the elements in a row in order of atomic weights, and starting a new row when the characteristics of the elements began to repeat. This resulted in the arrangement where the elements with similar properties occupied the same vertical column. Mendeleev termed these vertical columns as groups and resultant horizontal rows as series. Mendeleev's success roots to his vision of classifying elements based on the similarities in their empirical formulas and properties of the compounds formed by them. This made him to occasionally ignore the order suggested by atomic weights to classify elements with similar properties together. For example, iodine with lower atomic weight than that of tellurium was placed in group 7 along with fluorine, chlorine and bromine because of its similarities with their properties. Mendeleev also left gaps in the table for undiscovered elements. For example, he left gaps under aluminium, silicon and boron in the periodic table for yet to be discovered elements. He not only predicted the existence of these elements and called them Eka aluminium, Eka silicon and Eka boron respectively, but also described some of their general physical properties. These elements were later discovered and named as gallium, germanium and scandium. Mendeleev's confident predictions and their eventual success made his periodic table win accolades. However, there were certain anomalies in Mendeleev's periodic table. These anomalies were: 1. The position of hydrogen was not correctly defined. 2. There was no place for isotopes of elements in his periodic table. 3. The placement of elements having greater atomic mass before elements having lower atomic mass could not be logically explained. In the early 1900s, discovery of newer elements, isotopes, and the development of atomic theories paved way for the development of the modern periodic table. You have already learned that the anomalies in Mendeleev's periodic table paved way for the development of the modern periodic table. Mendeleev's periodic table was developed at a time when the internal structure of atoms was unknown. Discovery of subatomic particles and their properties took place at the start of 20th century. Isotopes and noble gas elements were also discovered around the same period. These discoveries warranted improvements in Mendeleev's periodic table. In 1913, an English physicist, Henry Moseley, observed regularities in the characteristic X-ray spectra of elements. On plotting the square root of X-ray frequency emitted by elements against their corresponding atomic numbers, Moseley got a straight line graph. However, he did not observe the same pattern when he plotted the same X-ray frequencies against their corresponding atomic weights. Based on his findings, Moseley established that the atomic number, which is the number of protons contained in the nucleus, or the number of electrons surrounding the nucleus in a neutral atom, is a more fundamental property of an element as compared to its atomic mass, as it defines the electronic structure and properties of an element. Hence, Moseley suggested that atomic number and not the atomic mass should be the basis of classification of the elements. Using Moseley's revelation, Mendeleev's periodic law was modified to modern periodic law. According to modern periodic law, the physical and chemical properties of the elements are periodic functions of their atomic numbers. This means that if the elements were arranged in order of their increasing atomic numbers, elements with similar properties would repeat after certain regular intervals. Thus, many anomalies of Mendeleev's table were removed. For example, the confusion about the position of isotopes was solved. Another anomaly, the placement of higher atomic weight elements like tellurium before lower ones like iodine, was also removed. However, the placement of hydrogen was one anomaly of Mendeleev's periodic table that was still not resolved. On the basis of its atomic number, Moseley placed hydrogen at the top left corner of the table without attaching it to any particular group. After Moseley modified the periodic law, several scientists drafted various forms of periodic tables that focused on factors such as chemical reactions, valence, and electronic configurations of elements. Of all these periodic tables, the long form of the periodic table, which is synonymous to the modern periodic table today, is the most convenient and widely used table. It arranges the elements in horizontal rows and vertical columns based on atomic numbers, while keeping electronic configuration as the basis for periodicity in the properties of elements. Similar to Mendeleev's periodic table, in the long form of periodic table, the horizontal rows were called periods and the vertical columns were called groups. The periods contain elements arranged according to their atomic numbers, and the groups contain the elements having similar outer electronic configurations in their atoms. It has a total of 7 periods based on the highest principal quantum number of the elements in that period. Each period contains specific number of elements as suggested by its principal quantum number. For example, first period has 2 elements. Second and third period have 8 elements. Fourth and fifth period have 18 elements. In both the sixth and seventh periods, only 18 elements are shown in the periodic table. Remaining 14 elements of each of these 2 periods are shown in separate panels at the bottom of the table and are referred to as lanthanoids and actinoids respectively. The number of groups total 18 and are numbered from 1 to 18 as per the IUPAC standards. Let's now understand the periodicity of properties in the modern periodic table. As the atomic number increases across the period, the outer electronic configuration changes gradually from one element to another, resulting in a corresponding gradual change in properties of elements. As the atomic number increases, metallic properties decreases and non-metallic properties increases. In a group, all elements have similar electron arrangement and therefore similar physical and chemical properties. For example, all the elements of 13th group in the periodic table have the outer electronic configuration Ns2Np1 and therefore share similar physical and chemical properties. For example, except for boron, all other elements are metallic, are readily found in minerals and ores, and their melting and boiling point decreases as we go down the group. As of July 2009, the long form of periodic table has a total of 118 elements. All the elements between uranium, atomic number 92, and fermium, atomic number 100, are called transuranium elements. The elements after fermium are called transfermium elements. Both transuranium and transfermium elements are man-made elements synthesized in laboratories using costly and sophisticated equipment. Traditionally, newly discovered elements were named either after their synthesizers or discoverers. For example, the element mendelevium, atomic number 101, was named after Dmitry Mendeleev. Similarly, nobelium, atomic number 102, and lawrencium, atomic number 103, were named after famous scientists Alfred Nobel and Ernest O. Lawrence, respectively. However, for the elements with atomic number greater than 103, different groups began to claim credit for the discovery of the same element, causing naming controversies. For example, both American and Soviet scientists claimed credit for discovering element 104. The Americans named it Rutherfordium, whereas Soviets named it Kurchatovium. To avoid such controversies, IUPAC suggested a systematic procedure to be followed for naming elements with atomic numbers greater than 100. They recommended that until the discovery of a new element is proved and its name is officially recognized, an element be named based on a systematic nomenclature. This nomenclature is formulated directly from the atomic number of the elements using the numerical roots for 0 and numbers 1 to 9. The roots are put together in order of digits, which make up the atomic number, with IUM appended to it at the end of the name derived. For example, an element with atomic number 118 should be named as ononctium from 1 is equal to UN, 8 is equal to oct, and IUM. And the first alphabet forms the temporary symbol of the element UUO. After the discovery of the new element is proved, it gets a permanent name and symbol by a vote of IUPAC representatives from each country. The permanent name, thus obtained, might reflect either the name of the country or its state, like germanium, californium, and bohrium. The long form of periodic table is the most widely used modern periodic table. It arranges all the known elements into 7 periods and 18 groups, based on their electronic configuration. Why use electronic configuration to decide arrangement of the elements? To find the answer to this question, let's first review what electronic configuration means. The term electronic configuration refers to the distribution of electrons in the shells and orbitals of an atom. The principal quantum number of a shell, n, defines the energy level of an electron and gives its distance from the nucleus. Shell is further divided into subshells. These are S, P, D, and F. The electronic configuration of an atom defines its physical and chemical properties. For example, as we go from left to right in a period, the atomic size keeps on decreasing. This happens because as the atomic number increases, more electrons get added to the same principal energy level. Due to the same effective distance of electrons from a more positive nucleus due to additional protons, electrons get more strongly attracted to the nucleus, thereby decreasing the atomic size. However, the principal quantum number increases as we go down a group, as the outer shells are more shielded from the nuclear attraction due to additional layer of electrons, and distance from the nucleus as compared to the previous level. This results in increasing atomic size with increase in atomic number. The chemical properties of elements depend on their electronic configuration for the same reason. The elements with higher principal quantum number more readily take part in chemical reactions due to weakly bound outer electron. The chemical reactivity, however, decreases with increase in atomic number for the set of elements having the same principal quantum number. Likewise, the other physical and chemical properties of elements, such as density, boiling and melting points, ionization energy, electron gain enthalpy, and electronegativity, also depend on their electronic configuration. These physical and chemical properties repeat periodically for elements having the same electronic configuration in their outermost shell, a trend that can be seen across the elements belonging to the same group in the long form of periodic table. The long form of periodic table arranges elements with the same principal quantum number n across a period, such that their electronic configuration changes only at the outermost shell. The number of elements in the period, therefore, depends on the maximum number of electrons that principal energy level or shell can accommodate. For example, the first period corresponds to the filling of electrons in the first energy shell or K shell, where n equals 1. Since this energy shell has only one orbital, 1s, it can accept a maximum of 2 electrons. Therefore, the first period has only 2 elements, hydrogen 1s1 and helium 1s2. The second period corresponds to the filling of electrons in the second energy or L shell, where n equals 2. It has a total of 4 orbitals, 1 2s and 3 2p, that can collectively accommodate 8 electrons. The second period starts with lithium with atomic number 3 and electronic configuration 1s2 2s1, ends with neon with atomic number 10. Neon has completely filled p shell and electronic configuration of 1s2 2s2 2p6. The third period corresponds to the filling of electrons in the third energy shell or M shell, where n equals 3. Although this shell has 9 orbitals, 1 3s, 3 3p and 5 3d orbitals, filling electrons in 3d orbitals is not energetically favorable as per Aufbau principle. You will learn more about this principle in the next module. Therefore, only 4 orbitals are available for filling electrons, which allow a maximum of 8 electrons in the outermost shell. As a result, there are 8 elements in the third period, starting from sodium, whose electronic configuration is 3s1, and ending with argon, whose electronic configuration is 3s2 3p6. The fourth period corresponds to the partial filling of electrons in the fourth energy level, where n equals 4. This is because, for this period, filling the 3d orbitals after the 4s orbitals and before the 4p orbitals becomes energetically favorable in accordance with the Aufbau principle. Therefore, this period contains 3d transition series of elements placed after potassium and calcium in the fourth period. The first element in the 3d series, scandium, has an electronic configuration 3d1 4s2. The last element in this series is zinc, having an electronic configuration 3d10 4s2, wherein the 3d orbital is completely filled. The fourth period ends with the element krypton with atomic number 36 and completely filled 4p orbitals. The fifth period corresponds to the filling of electrons in the fifth energy shell, where n equals 5. This period contains 4d transition element series, which starts with yttrium that has an atomic number 39 and ends with cadmium with atomic number 48. The first element in the 4d series, yttrium, has an electronic configuration 4d1 5s2. The last element in this series is cadmium, having an electronic configuration 4d10 5s2, wherein the 4d orbital is completely filled. In the fifth period, electrons enter into the 5s, 4d and 5p orbitals successively. The fifth period ends with xenon with atomic number 54 and completely filled 5p orbitals. The sixth period corresponds to the filling of electrons in the sixth energy shell, where n equals 6. It contains a total of 32 elements and follows the orbital sequence of 6s, 4f, 5d and 6p. This period contains the 4f inner transition series of elements after cesium and barium, also called the lanthanoid series. The lanthanoid series starts at cerium and ends at lutetium. The seventh period consists of most of the man-made radioactive elements that have 7s, 5f, 6d and 7p orbitals filled. This period also contains 32 elements, including the 5f inner transition series called the actinoid series. The actinoid series starts at thorium and ends at lawrencium. It may be interesting to note that the number of elements in each period is twice the number of atomic orbitals available in the energy level that is being filled. For example, in the first period, only one atomic orbital is filled, hence the number of elements is 2. In the second and third periods, 4 atomic orbitals can be filled, therefore the number of elements is 8. In the fourth and fifth periods, 9 orbitals can be filled, hence the number of elements is 18. And in the sixth and seventh periods, 16 orbitals can be filled, and hence the number of elements is 32. The classification of elements across periods results in vertical columns of elements that have similar outer electronic configuration, same number of valence electrons, and therefore similar properties. In other words, they belong to the same family or group. For example, all the elements in group 1 of the periodic table have ns1 valence shell electronic configuration. Due to the presence of same number of valence electrons, all elements of this group are alkali metals that show similar properties. The only group that could have distorted this characteristic of all elements in a group having similar properties is group 3, that contains the lanthanoid and actinoid series of elements in periods 6 and 7. To avoid this discrepancy and to maintain the structure of the periodic table, these series are placed separately below the periodic table, thereby preserving the principle of classification. Thus, the long form of periodic table is in perfect accordance with the modern periodic law, keeping electronic configuration, which in turn depends on atomic number, as the basis of classifying elements. We had studied that the position of an element in the periodic table is based on its valence shell electronic configuration, based on the type of atomic orbitals which receive the last electron or differentiating electron. These elements are categorized as S, P, D, and F block elements. However, there are two exceptions to this classification. The first exception is helium. Based on its electronic configuration, it should be placed in the S block in the periodic table. But it is placed in the P block with the other group 18 elements. This is because, like other group 18 elements, helium has a completely filled valence shell and as a result exhibits characteristic properties of other noble gases. The other exception is hydrogen, which has only one electron in the s orbital, and therefore can be placed in group 1 with other alkali metals. However, hydrogen can also gain an electron to achieve the nearest noble gas configuration of helium, and hence can be placed along with halogens in group 17. Therefore, it is considered as a special case and is placed separately on the top of the periodic table. Let's now learn about the S block elements. The S block of the periodic table consists of elements that have the last electron entering the ns orbital. The alkali metals in group 1 and the alkaline earth metals in group 2 of the long form of the periodic table belong to this category. These are soft metals with low melting and boiling points. With the valence shell electronic configuration of ns1 and ns2 respectively, these elements have extremely low ionization enthalpies. That is, they easily lose their outermost electrons to form unipositive ions in the case of alkali metals, or dipositive ions in the case of alkaline earth metals. Therefore, the compounds formed by the S block elements, with the exception of those formed by lithium and beryllium, are ionic in nature. Due to low ionization enthalpies, S block elements are highly reactive and therefore are never found in pure form in nature. They always occur in combined form in nature. For example, magnesium occurs in the combined state as carbonates, sulfates, chlorides, and silicates, but never as pure magnesium. The metallic character and chemical reactivity of S block elements increases as we go down the group. Now let's discuss the properties of the P block elements. The elements of group 13 to 18, situated at the right side in the long form of periodic table, belong to this block. The P block elements, together with the S block elements, are called the representative elements or main group elements. The P block elements have their last electron entering the p orbital. This results in an outermost electronic configuration varying from ns2 np1 to ns2 np6 in each period. At the end of each period is a noble gas element with a stable configuration of ns2 np6. The P block consists of metals, nonmetals, and metalloids. The non-metallic character increases across a period and the metallic character increases as we go down the group. The p-block elements form compounds by loss or gain of electrons, or by sharing the valence electrons. That is, they form both ionic as well as covalent bonds. Two chemically important groups of p-block elements are Group 16, the chalcogens, and Group 17, the halogens. The elements of these two groups have high negative gain enthalpies, and they readily gain one or two electrons to attain the stable noble gas electronic configuration, which is Ns2np6. For example, chlorine, belonging to the halogen family, readily accepts one electron to attain the nearest inert gas configuration of argon. On the other hand, oxygen belonging to the chalcogen family needs to accept two electrons to attain the inert gas configuration of neon. The group 18 elements having the electronic configuration Ns2np6 are called the noble or inert gases. All of them exist as monoatomic gases. Noble gases exhibit very low chemical reactivity because of their completely filled outermost shell. Next, let's look at the d-block elements. The elements belonging to group 3 to 12 in the center of the periodic table are called the d-block elements. As the differentiating electron or the last electron enters into the penultimate or second outermost shell, that is, the n-1 d orbital, they are referred as d-block elements. These elements have an outermost electronic configuration of n-1 d1 to 10 ns1 to 2. The d-block elements are placed between the s and p-block elements. They exhibit the transitional or intermediate behavior between the more active metals in S block and less active elements in the P block, and are hence called transition elements. Small size of atom, high nuclear charge and unpaired electrons in d orbitals impart characteristic properties to the transition elements. These properties are: all the transition elements are metals, and they exhibit variable oxidation states. Due to their ability to change oxidation states, most of these transition metals and many of their compounds are used as catalysts in many industrial processes. For example, iron is used as a catalyst in the Haber process for the synthesis of ammonia. Similarly, nickel is used as a catalyst for hydrogenation of oils. Most transition metals form colored compounds. For example, MnCl2 is a pink-colored compound, while ferrous sulfate is a green-colored compound. These elements and their ions are usually paramagnetic. That is, they are attracted to external magnetic fields because of the presence of unpaired electrons in their d orbitals. For example, the elements iron and nickel and their ions Fe+3 and Ni+2 exhibit paramagnetism. It is important to note that zinc, cadmium and mercury are not considered as transition elements, as they do not share the usual characteristics of transition metals. This happens because, unlike other transition elements, these elements have completely filled d orbital with electronic configuration of n-1 D10NS2. At the bottom of the long form of periodic table, there are two rows of elements that belong to the F block. These elements have their last electron entering the f orbitals and exhibit an outer electronic configuration of n-2, f1 to 14, n-1, d0 to 1, ns2. Since f orbitals are present in the antipenultimate shell, or the shell inner to the penultimate shell, these elements are also called inner transition elements. There are two series of F-block elements with 14 elements each. The elements in which the differentiating or the last electron enters into the 4 f orbitals are called lanthanoids, whereas the elements in which the last electron enters into 5 f orbitals are called actinoids. They are all metals with high melting and boiling points. Like transition metals, they too form colored salts and exhibit variable oxidation states, the most common oxidation state being 3+. Actinoids can exhibit a much larger number of oxidation states as compared to lanthanoids. Therefore, they have a more complex chemistry. Unlike the lanthanoids, actinoids are radioactive in nature. Very few of them, like thorium, uranium, occur in nature, and most of them are artificially made by nuclear reactions. The elements after uranium are called trans-uranium elements. Apart from classifying elements into S, P, D, and F blocks, the periodic table also shows the classification of elements into metals, nonmetals, and metalloids. Metals have been listed on the left side of the table and form 78% of the known elements. Metals generally exist as solids at room temperature. An exception is mercury, which is liquid at room temperature. Metals usually have high melting and boiling points. With the exception of gallium and cesium, which have very low melting points of 303 Kelvin and 302 Kelvin respectively. Metals are good conductors of heat and electricity. Metals are malleable, that is, they can be flattened into thin sheets and are ductile, which means they can be drawn into wires. These properties are in direct contrast to those exhibited by the nonmetals that are placed on the top right side of the periodic table. Nonmetals are usually solids or gases at room temperature with low melting and boiling points. Exceptions are boron and carbon, which have high melting points of 2300 and 3930 degrees Celsius respectively. It is also important to note that bromine is the only nonmetal that exists in liquid state at room temperature. They are poor conductors of heat and electricity. Solid nonmetals are brittle, non-malleable, and non-ductile. Across a period, as we move from left to right, there is a transition from the metallic behavior to the non-metallic behavior. Elements like silicon, germanium, arsenic, antimony, and tellurium in the P block of the periodic table exhibit properties of both metals and non-metals, and therefore are called semi-metals or metalloids. You are already aware of the periodic trends in the fundamental physical properties such as atomic or ionic radii, ionization enthalpy and electron gain enthalpy of elements. Let's now see how the periodicity in these properties is related to the periodicity in the chemical reactivity of elements. While moving from left to right in a period, the atomic and ionic radii decreases. As a result, the ionization enthalpies increase and the electron gain enthalpies become more negative across a period. In other words, alkali metals of group 1 have the lowest ionization enthalpies, and halogens of group 17 have the most negative electron gain enthalpies. Low ionization enthalpy, as in the case of alkali metals, means that the elements are willing to give away their most loosely bound electrons. In other words, alkali metals are good reducing agents and are highly reactive in nature. The most negative electron gain enthalpy being attributed to halogens indicates that halogens behave as good oxidizing agents and exhibit high chemical reactivity. This is in contrast to the noble gases that have completely filled outer electronic shells and thus exhibit a positive electron gain enthalpy and the least reactivity. Chemical reactivity is the highest for both alkali metals and halogens. The maximum chemical reactivity at the extreme left of a period among the alkali metals is due to the lowest ionization enthalpy, which enables it to lose an electron that leads to the formation of a cation. On the other hand, the maximum chemical reactivity at the extreme right among halogens is due to the highest electron gain enthalpy, which facilitates an atom to gain an electron, leading to the formation of an anion. This property of forming cations and anions can be related to the oxidizing and reducing behavior of the elements. The chemical reactivity of an element is best shown by its reactions with oxygen and halogens. The alkali metals and halogens show a higher tendency to combine with oxygen as compared to the elements in the center. The oxides formed by the elements on the extreme left of a period are basic, while those formed by the elements on the extreme right are acidic in nature. For example, sodium, a group 1 alkali metal, forms sodium oxide with oxygen, which on reaction with water forms a base called sodium hydroxide, NaOH. In contrast, chlorine, a group 17 halogen, on reaction with oxygen, forms a highly acidic oxide called chlorine heptaoxide, which on reaction with water forms perchloric acid. Oxides formed by elements in the center are either amphoteric, like aluminium oxide, or neutral, like carbon monoxide. Amphoteric oxides can behave both as acids and as bases depending upon whether they react with a strong base or a strong acid. Neutral oxides, on the other hand, are neither acidic nor basic. The trend of oxides of the third period is observed as from strongly basic to weakly basic to amphoteric to weakly acidic to strongly acidic. Let's now consider the chemical reactivity down a group in the periodic table. The atomic and ionic radii typically increase down a group. As a result, for representative elements, the ionization energies gradually decrease and electron gain enthalpies become less negative down a group. Also, the metallic character increases down the group while the non-metallic character decreases down the group. Therefore, the chemical reactivity increases down a group for alkali and alkaline earth metals, while it decreases for halogens down the group. In the transition metals in the third series of the periodic table, the change in atomic radii is much smaller as compared to those for representative elements across the period. Similarly, the inner transition series 4F and 5F elements show even smaller variation in atomic radii. The ionization enthalpies of the transition and the inner transition elements are intermediate between those of S and P blocks. As a consequence, they are less electropositive than group 1 and 2 metals. A gradation in their physical and chemical properties is attributed to the arrangement of elements with respect to their electronic configurations. In this particular module, you will learn about the periodic trends in physical properties such as atomic radius, ionization enthalpy, electron gain enthalpy, and electronegativity. The first important physical property is atomic radius. Atomic radius can be defined as the distance from the center of the nucleus to the point up to which the density of electron cloud is maximum. Measuring the actual atomic radius is a difficult task for two reasons. First, the size of an atom is of the order of 1.2 angstrom or 1.2 multiplied by 10 to the power of minus 10 meters, which is too small to be precisely measured. Secondly, the electron cloud surrounding an atom does not have a well-defined boundary, which again adversely affects the precision of the measurement. However, it is possible to estimate the radius or size of an atom by knowing the distance between the atoms in a combined state. Depending on the nature of bonding, atomic radii are of three types. They are covalent radius, metallic radius, and van der Waals radius. Let's learn about each of them in detail. Covalent radius is a general term which is used in reference to non-metals. A covalent radius is 1/2 of the distance between the nuclei of two atoms, held together by a covalent bond in a homodiatomic molecule. For example, the internuclear distance between the chlorine atoms in the chlorine molecule is 198 picometers. Therefore, the radius of a chlorine atom is the half of this distance, which is 99 picometers. For metals, we use the term metallic radius. Metallic radius is half the internuclear distance between the centers of the nuclei of two adjacent metal atoms in a metallic crystal. For example, the distance between two adjacent copper atoms in solid copper is 256 picometers. Therefore, the metallic radius of copper is 128 picometers. Atomic radii of both the types, covalent and metallic, are usually measured by X-ray or by other spectroscopic methods. Let us now see the variation of atomic radii across the periodic table. Generally, atomic radius decreases across a period and increases as we go down a group. The table lists the atomic radii of few elements from the second and third periods of the periodic table. A decrease in atomic size across a period is due to the increasing effective nuclear charge with increase in atomic number. Nuclear charge is the net positive charge experienced by an electron of an atom. The effective nuclear charge varies with the proximity of electrons from the nucleus. This is because electrons in the inner orbitals shield the electrons in the outer orbitals from experiencing the full nuclear charge. For example, the valence electron in cesium is shielded from the nucleus by the inner electrons. As a result, the valence electron experiences a net positive charge that is less than the actual charge. Across a period in the periodic table, as we move from left to right, the nuclear charge increases by 1 unit in each succeeding element, while the principal energy level remains the same. As a result, the effective nuclear charge increases, and the electrons in the valence orbital get more strongly attracted to the nucleus, reducing the size of the atom. Down the group, the atomic radius increases with the atomic number. As we move down the group, a new energy shell is added to each succeeding element. In other words, the principal quantum number n increases down the group, and the distance between the valence electrons and the nucleus increases. As a result, the shielding provided by the electrons in the inner energy levels becomes more effective, especially if the inner orbitals preceding the valence electrons are full, as in the case of alkali metals and halogens. Therefore, the size of the atom increases down a group. According to the atomic size trends explained so far, the noble gases should have the smallest sizes, as they are the last elements in each period. However, the atomic radii of noble gases are not considered here. Noble gases, being monoatomic, have very large non-bonded radii values. Hence, the radii of noble gases should be compared with the van der Waals radii of other elements, rather than the covalent radius. Van der Waals radius is half the internuclear distance between two non-bonded neighboring atoms or two adjacent atoms belonging to two neighboring molecules of an element. Van der Waals radii are usually larger than covalent or metallic radii. The radius of an atom changes when it loses or gains an electron to form an ion, and the resultant radius is called ionic radius. Ionic radii exhibit the same trend as the atomic radii. When an atom loses an electron, it forms a positive ion called cation. The radius of a cation is always smaller than its parent atom because, while the nuclear charge remains the same, the number of electrons is decreased. This results in increase in the nuclear attraction on the valence electrons, leading to decrease in the size of the atom. For example, the atomic radius of sodium atom Na is 186 picometers, whereas the ionic radius of sodium ion Na+ is 95 picometers. Similarly, when a parent atom gains an electron, it forms a negative ion or an anion. The addition of one or more electrons results in an increased magnitude of inter-electronic repulsions among the electrons and a decrease in the effective nuclear charges. Therefore, the size of an anion is larger than that of the parent atom. The atomic radius of fluorine, F, is only 64 picometers, whereas the ionic radius of fluoride ion F- negative is 136 picometers. Clearly, the variation between the atomic and ionic radius depends on the effective nuclear charge. This is why the ions belonging to isoelectronic series have different ionic radii, Isoelectronic species may be defined as atoms and ions which contain the same number of electrons but differ in nuclear charge. Within a series of isoelectronic species, as the nuclear charge increases, the force of attraction by the nucleus on the electrons also increases. As a result, ionic radii decrease. For example, N-3, O-2, F-, Na+, Mg+2 and Al+3 ions have the same number of electrons, that is 10. However, their radii would be different because of their different nuclear charges. As cation with greater positive charge has smaller radius and anion with greater negative charge has larger radius, the order of ionic radii among the isoelectronic species increases in the order as shown here. Another important physical property is ionization enthalpy. The energy required to remove the most loosely bound electron from an isolated gaseous atom, X, in its ground state is called ionization enthalpy. Ionization enthalpy is expressed in the units of kilojoules per mole. Energy is always required to remove electrons from an atom, and hence ionization enthalpies are always positive. The energy required to remove the most loosely bound electron is called the first ionization enthalpy. The energy required to remove the second and the third electron is termed as the second ionization enthalpy and the third ionization enthalpy respectively. The second ionization enthalpy will always be higher than the first ionization enthalpy. This is because, on removing an electron, the unipositive ion formed will have more effective nuclear charge. Due to this, the nuclear attraction on the electrons increases, and hence, more energy is required to remove an electron from the unipositive ion. The term ionization enthalpy, if not specified, is taken for the first ionization enthalpy. The graph shown here depicts the variation in first ionization enthalpies delta IH of the first 60 elements in the periodic table. As you can see from the graph, noble gases with stable NS2-NP6 configuration have the maximum first ionization enthalpies and hence are chemically inert. The alkali metals with one electron in their valence shell, on the other hand, have the lowest first ionization enthalpies and hence are highly reactive. The ionization enthalpy generally increases across a period because of the decrease in atomic size. In general, as we move from left to right in a period, successive electrons are added to the same shell. As a result of this, the nuclear charge increases while the shielding effect remains almost the same. Thus, across a period, the increasing nuclear charge outweighs the shielding effect. As a consequence, the outermost electrons are held more tightly, resulting in the decrease in size, and thus increase in ionization enthalpy across the period. However, there are a couple of exceptions to this guideline. To illustrate this, let's consider the first ionization enthalpies of the second period. The first ionization enthalpy of boron is slightly less than that of beryllium, even though the former has a greater nuclear charge. This happens because in the case of beryllium, the 2s orbital is completely filled, and moreover, the electrons are present in the more penetrating s orbital. On the other hand, in boron, the outermost electron is unpaired and is also present in the less penetrating p orbital. Hence, more energy is required to remove a 2s electron from beryllium than to remove a 2p electron from boron. The other anomaly is the smaller first ionization enthalpy of oxygen as compared to nitrogen. In the case of nitrogen, the 3 2p electrons reside in different atomic orbitals in accordance with the Hund's rule. The half-filled orbitals confer extra stability to the nitrogen atom. However, in the oxygen atom, 2 of the 4 2p electrons occupy the same 2p orbital. This results in increased electron-electron repulsion. Hence, it requires less energy to remove the 4th 2p electron from oxygen than to remove one of the 2p electron from the stable half-filled nitrogen atom. Let's now discuss the variation of ionization enthalpy down the group. As we go down a group, although the nuclear charge increases, the size of an atom and the shielding effect also increases with the increase in the number of shells. Due to this, the nuclear attraction on the outermost electron is decreased. Thus, removing such an electron requires less energy, and hence, ionization energy decreases down a group. Let's look at yet another important physical property: electron gain enthalpy. It is the measure of the ease with which an atom can gain an electron and form an anion. The enthalpy change during the process of addition of an electron to a neutral gaseous atom to convert it into a negative ion is defined as the electron gain enthalpy. The process of adding an electron can be either endothermic, that is, energy absorbing, or exothermic, that is, energy releasing. It is exothermic when an element reaches a more stable state by the addition of an electron. For example, halogens attain a stable noble gas electronic configuration after gaining an electron. Hence, they have very high negative electron gain enthalpy values. On the other hand, noble gas elements have large positive electron gain enthalpies. This is because, in the case of noble gases, the electron has to enter the next higher principal quantum level, leading to a very unstable electronic configuration. Therefore, noble gases need to absorb energy in order to gain an additional electron. The variation in electron gain enthalpy of elements in the periodic table is not as systematic as the ionization enthalpies. Generally, electron gain enthalpy becomes more negative with each successive element across a period. In other words, electron affinity increases across a period. This is because, as we move from left to right across a period, the effective nuclear charge increases and the atomic size decreases. The addition of a new electron would be easier for a smaller atom because the added electron would be closer to the positively charged nucleus. The electron gain enthalpy decreases down a group because of increase in the size of the atom, and also the added electron would be further away from the nucleus. However, there are exceptions to this rule. For example, the electron gain enthalpy of oxygen is less negative than that of the succeeding element sulfur. And the electron gain enthalpy of fluorine is less negative than that of the succeeding element chlorine. This is because oxygen and fluorine atoms are smaller in size and have strong inter-electronic repulsions. During the addition of an electron to these atoms, the electronic repulsions are overcome at the expense of some liberated energy, and hence, the overall energy liberated is less in these atoms. However, for the subsequent elements, sulfur and chlorine, the electron gets added to n is equal to 3 quantum level. At this quantum level, there is larger space available, which reduces the electron-electron repulsion, thereby making the addition of the new electron easier. Another physical property of elements in the periodic table, usually confused with electron gain enthalpy, is electronegativity. It is the ability of an atom in a chemical compound to attract shared pair of electrons towards itself. It differs from ionization enthalpy and electron gain enthalpy, as it is the property of the atom in the bonded state and not in the isolated gaseous state. Electronegativity is a qualitative term that was devised by L. Pauling for better understanding of covalent bonds and their polarity. Although electronegativity is a qualitative measure, different scales have been developed to measure it, such as Pauling scale, Mulliken-Jaffe scale, and Aldred-Rochow scale. Of these scales, the Pauling scale, named after its discoverer Linus Pauling, is the most widely used scale to measure electronegativity. Pauling assigned an arbitrary value of 4.0 to fluorine. The table shows the approximate value for the electronegativity of few elements based on the Pauling scale. The higher the difference in the electronegativity of two bonded atoms, the more is the probability of the bonding electron pair to localize around the more electronegative atom. For example, in the case of water, oxygen being more electronegative pulls the shared pair of electrons closer to itself. As a result, the hydrogen atoms in water are slightly electron deficient, whereas the oxygen is electron-rich, causing an overall dipole moment in water. Electronegativity increases across a period. The increase in electronegativity across a period is due to the increase in effective nuclear charge. Smaller atoms have high electronegativity values than the bigger atoms. The larger the size of the atom, the lesser the tendency to attract the shared pair of electrons. This is why electronegativity decreases down a group. As shown here for the group 1 elements. The noble gas elements have zero electronegativity due to the stable octet configuration in their outer shells. Non-metallic elements have stronger tendency to gain electrons. Thus, electronegativity increases with the increasing non-metallic nature of elements across a period. as the elements down a group exhibit increasing metallic nature. The electronegativity also decreases. You have learnt that the reoccurrence of similar outermost electronic configuration after certain regular intervals causes periodicity in the physical properties of elements. Now let's see how periodicity affects the chemical properties of elements. Oxidation state is one of the periodic properties of an atom. According to IUPAC, an oxidation state can be defined as a measure of the degree of oxidation of an atom in a substance. In simpler terms, it can be defined as the number of electrons that have been removed from an element called positive oxidation states, or the number of electrons that have been added to the element, called negative oxidation states. So, the oxidation state of a monoatomic ion is equal to the net charge on the ion, positive or negative. The oxidation state of any element in the uncombined form is 0. So, oxidation states are typically represented by integers that assume positive, negative, or 0 values. How do you calculate the valence or oxidation states of elements? They can be deduced from the outer electronic configurations of elements. For representative elements, it is usually equal to the number of electrons in the outermost shell and or 8 minus the number of outermost electrons. As can be seen from the table, for representative elements belonging to groups 1, 2, 13, and 14, the oxidation states shown by elements is given by the number of valence electrons. However, for groups 15 through 17, the oxidation states are given by number of electrons in the outermost shell and or 8 minus the number of valence electrons. Transition and inner transition elements exhibit variable oxidation states. Along with transition, elements also show the oxidation states of inner transition elements. Now, let's understand the role of oxidation states of individual elements during the formation of compounds. The number of atoms of each element required for compound formation depends on the oxidation states of the elements. For example, magnesium belongs to group 2 and therefore shows an oxidation state of +2, whereas oxygen belonging to group 16 has an oxidation state of -2. Therefore, one atom each of these two elements are required to form a compound. Hence, the formula of magnesium oxide will be MgO. Note that magnesium oxide is an ionic compound, where magnesium loses electrons and oxygen gains electrons. Also note that the sum of the oxidation numbers of all the atoms or ions in a neutral compound like magnesium oxide is 0. But what happens in case of covalent bonding, where elements only share electrons, not gain or lose electrons? The oxidation state exhibited by an element in a covalent bond is equivalent to the charge acquired by its atom based on its electronegativity with respect to other atoms in the compound. The more electronegative element in a compound is given a negative oxidation state, whereas the less electronegative one is given a positive oxidation state. For example, in case of chlorine oxide, oxygen has a greater electronegativity as compared to chlorine. Therefore, oxygen atom shows an oxidation state of -2, whereas the two chlorine atoms show an oxidation state of +1 each. Now, let's take the case of oxygen difluoride. Recall that fluorine is the most electronegative element on Pauling scale, and therefore has a greater electronegativity than oxygen. Therefore, when fluorine combines with oxygen, the two fluorine atoms show an oxidation state of -1 each, and oxygen shows an oxidation state of +2. Some elements always have the same oxidation state in their compounds, with few exceptions. As we move from left to right in the periodic table, the oxidation number of the elements first increases and then decreases. As explained earlier, the oxidation number in a group remains constant and depends on its generic electronic configuration. The number of oxidation states, however, is the individual property of each group. You can observe periodic trends in the oxidation states of elements based on the formulas of their compounds, with hydrogen and oxygen. As true for oxidation states, all the elements in a group of periodic table show similar chemical properties. However, the elements in the second period do not share many periodic trends with their other group members. These elements include lithium in group 1, beryllium in group 2, and boron to fluorine in groups 13 to 17. Lithium in group 1 forms covalent compounds unlike other alkali metals that primarily forms ionic compounds. The behavior of lithium is more similar to the second element of group 2, magnesium. Similarly, beryllium behaves more like aluminium, which is placed in the third period and group 13. This similarity in properties found amongst the elements that exist diagonally to each other in the periodic table is called diagonal relationship. This anomalous behavior of second period of elements is because of three main reasons. 1. Small size. 2. Large charge to radius ratio. And 3. High electronegativity of elements. Small size means greater attraction between the nucleus and the valence shell electrons. So while forming compounds, the atom tends to share its electrons with other atoms, rather than losing them completely. Large charge to radius ratio means that the ion of the atom has a higher charge sitting on small-sized atom, a condition that favors covalent bonding. High electronegativity means that the atom has a higher attraction for shared electrons. This again makes covalent bonding favorable. In addition to the previous reasons, the availability of lesser valence orbitals and the peculiarity of the bonding capabilities of second period elements also contribute to their anomalous behavior. The first member of each group has only 4 valence orbitals, 1 2s and 3 2p orbitals available for bonding, whereas the second member of the groups have 9 valence orbitals, 1 3s, 3 3p and 5 3d orbitals. As a result, the maximum covalency, or the number of shareable electron pairs, of the first member of each group is 4, whereas the other members of the groups can expand their valence shell to accommodate more than 4 pairs of electrons. For example, boron can only form single charge ion with fluorine, whereas aluminium can form higher charged ions with fluorine. In addition, the first member of p-block elements has special bonding capabilities as compared to the other members in the group. They have a tendency to form multiple bonds, as in the case of carbon and nitrogen, and to other second period elements compared to subsequent members of the same group.